welcome to the fourth day of the workshop. How are you? Are you still full of energy? Okay, very good. Welcome for those who are online too. Today we'll start with the talk by Mr. Chris Rokaukas. Am I pronouncing this right? Yeah. On scientific machine learning. And Chris is a research affiliate and co-PI of the Julia Lab at the Massachusetts Institute of Technology, director of modeling and simulation at Julia Computing and Creator. He's a lead developer of Julia Sim Director of Science Research at Pumas AI and creator, lead developer of Pumas of the SciML open source software organization. Thank you very much.
Yep, thank you very much. So, just as a show of hands, who here is like a common user of Julia? Because I think that this is not as much of like a use Julia a lot kind of crew, right? So I want to just start at the very beginning of So what I want to get into is a form of machine learning that is incorporating a lot of prior scientific information. But my normal talk tends to be what I would call math, what most people call gibberish. So I'm kind of going to start at a different point here, which is like, what are we doing with Julia? Why is it interesting? And what are some of the things that we're doing with scientific machine learning? Kind of inspire the whole point behind it, right? So what are we doing? So what is Julia, right? So Julia is a programming language. It normally started back in 2012. Though most people did not know about it until quite later, right? So the 2018 time, that's when Julia 1.0 came out, and the key with that though is around the 1.0 time frame, we had a lot of projects that started to come. If you think about it, that's around the same time they had this kind of upswing in machine learning, right? And so we had a lot of companies starting to come out at the same time that were fully using Julia for doing scientific machine learning. So you can see up there, one of our big ones early on was things like Flux for pharmaceutical simulation. So for example, the company Erna was done with using different equations and the techniques that we'll talk about. And then we're working in a lot of spaces like aerospace, in industries like hydraulics and industrial robots. We're being able to bring this kind of interesting connection between science and machine learning into all of these different areas, right? So there's a lot of different areas that we're really working on. And so, why are we doing these things with Julia? Before I get into the whole part of the talk, I think that this is a great slide because it's a slide that we did not make in the Julia community. Another programming language made this, but they still showed us as doing really well, which means that that's a pretty good result, right? So what is it showing, right? So you have one axis, which is how expressive the language is, right? What I mean by expressive is how small of a code you can have that solves the given problem, right? And then another one here is how faster it is, right? That's the y-axis. So if it's lower on the y-axis, that is log scale in terms of performance, right? So going down one line in there, you're going down by execution time from a minute to seconds, right? And now what you can see from that is that Julia is a language for which very small bits of code runs very fast. You have languages that are very easy to write. If you see Python, it's way up there. It's expressive, but the code behavior is slow, right? And then you also have languages like C, that's way down there in the the code that you write is always going to be fast, but it takes a long time to write this code. But Julia has this kind of mixture of the simple code that you write is also fast. And that's why we're going to be using it for a lot of these different applications here. And so, Julia, I think not everyone has adopted it yet, but there is this pretty strong community. The downloads are in the millions, right? Forum views are in the millions. I mean, there's an estimated about 1 million programmers using Julia right now. In the grand scheme of things, there's hundreds of millions of people doing programming or doing certain things on computers these days. So it's still not one of the most popular, but it is up there. It reached like top 20 in the popularity rankings, and it's still on this kind of large growth path, right? In fact, one of the things that's been pointed out about Julia was that it was, for example, by Stack Overflow. If you know Stack Overflow, they answer every undergraduate student's homework questions these days, right? Now, one of the most loved questions on there is, fifth, according to Stack Overflow, was Julia, right? According to their survey. Number 6 was Python. Number 28 was R, and poor MATLAB is down there in number 36. Maybe you shouldn't say poor MATLAB there. Their lawyers might come after us. But there's a lot of people who have adopted Julia throughout the universities. These are just some places are taking place in. There are many others that I did not list here. So it's something that a lot of people are using. I wouldn't say it's the standard, but it's one of the three that people kind of talk about these days, right? Julia, Python, and R. In fact, Jupyter Notebooks stands for Julia, Python, R for that reason, right? So that's just like a quick high level intro before I get into any, the what are we concretely doing. Now, the core point that I want to make part of this talk now is mixing machine learning with modeling simulation can make your data, can chop off the there. It can make your data a lot more efficient, right? And what do I mean by efficient? You can get a lot more insight out of the same amount of data. So first of all, before I even get into this, I've been talking with everyone at the lunches and such. Not everyone here is into has done a lot of machine learning, right? So I want to give a very biased view of what machine learning is to kind of lean you into what scientific machine learning is, right? So what is the start of machine learning? Well, it's a linear regression, right? So what are you doing when you are learning? Well, first of all, you do two things, right? First, you assume a functional form. So you say, out there in the world, when I have the number of phytoplankton inside of the water, or the concentration of phytoplankton, then I have an amount of fish that ends up in the water, right? And you ask a question. How are those two variables related, right? So you have a variable y, which is the number of fish, and you have a variable x, which is the amount of phytoplankton in the water, and you say y equals f of x. Let's learn this, right? This is the core of what machine learning is all about. It's just learning a function. So the very basic form of this is you assume the functions align, right? So what is a line? It's y equals ax plus b. Again, this is the non-math version of my talk, so we'll see how this goes. But so assume what you basically say is you say, okay, let's just assume that the answer is a line, and if the answer is a line, all we have to do is we have to learn what is the slope and where does that slope hit the y-axis, right? And so, you might have learned this in your classes, like, oh, this is linear regression. But in terms of a higher level understanding, what you're doing is you're making an assumption about the world, that the amount of fish is linearly related to the number of plankton in the ocean. And so it gives you that function, and find the values of the slope and where it hits the line. So that way that function goes through your data the best, right, under some definition of the best. So that's the start of machine learning. Let's find lines that relate data points. But there's no reason why it has to be a line, right? You can choose another function. So what's the next function that you learn in elementary school or whenever you learn this? You say, okay, well, I have a quadratic function, right? I can add a square term in front of that, and now I say this is a bit more complex of a function, right? How do I know this is more complex of a function? Well, if I make a equal to 0, it's a line, right? So it's at least this is more than a line, right? And I can say now I have 3 values. I can fit those 3 values so that way I put a line through the data, right? So now I could say, the relationship between how much fish I expect to have in the water given the amount of phytoplankton in this area is some quadratic function, right? But why stop there, right? Why stop there? You could do a cubic, right? There's a 3 now in front, right? So now we have 4 values to fit. So as long as then we can find a cubic function that fits our data. Why stop there? You can go to the 4th power, the 5th power, right? So you basically what you're doing then is you can say, well, maybe there's some relationship going on in the world, and I want to find the math that relates one thing to the next thing. So what I'm going to is relationship. Bringing into this process, we assume that there is a mathematical relationship between 2 entities, and we find a function that fits them. Now, here, this is just a quadratic, cubic, and we can go to high power as 1. But, what is the significance, though, of now starting to say, oh, it could be any polynomial? Well, the significance is, again, this is the non-math version of the talk. The significance is that any sufficiently nice function can actually be represented as a polynomial, right? Okay, in math courses, you prove that there are functions that you can't do Taylor series expansion. Just ignore your math professor for now. We're only looking at nice things, right? So the theorem, any sufficiently nice function can be represented by a Taylor series expansion, right? So, let's say you have some relationship out there in the world. Y equals you have y, and you have x, and you want to find out how these 2 things are related in your data, right? You can assume that there's a function that you could write in terms of a polynomial that approximates that. Why can you do that? Well, because pretty much every function you've ever that exists can be written out as a polynomial. You just need to have it as a highly degree polynomial, and you'll get there, right? That's what the Taylor theorem is going to describe for sufficient functions, right? And so what this means is that the process of learning a function y equals f of x. Oh, yep. And what this means then is that the process of learning a function y equals f of x is really a process of a function that is expressive enough to go capture the functions that you're looking to learn, and then learning the values that go into there. Like, what's the value that goes in front of x to the fourth? What's the value that goes in front of x to the third? There's just a bunch of numbers, like parameters in there. And you just want to learn the numbers that go in there, such that the line that you get goes through your data points, right? And now this is an interesting form because, polynomials, if they can fit pretty much any function, then you don't really need to kind of, if you think about what's going on in nature, right, you can start to say, well, maybe I think that this has a line between them, maybe this has a cubic between them. But if you start to do this, you could go, I really don't care what there is between them, right? Maybe it's a sine function or something, but anything can be represented in terms of a large polynomial. So let's learn what that large polynomial is, and now I've learned something that predicts the data, right? So this is all one-dimensional, though, right? This is just amount of fish that comes from phytoplankton. But now let's talk about something multivariable, right? So instead, you might want to go, okay, I have the amount of fish that are in this area as a function of the amount of phytoplankton, the sunlight, the latitude. There's now I have n different variables, and I want to predict what comes out of that. Well, where do you start? Where you start is you just say, I'm just going to build a line that is linear in every single one of my variables, right? I'm going to say there's a slope that is related to variable 1, a slope that's related to variable 2, a slope that's related to variable n, right? So how do you find out how to do, how do you find out this line that goes through everything? Well, that's what your stats course probably told you, right? This is the multivariate regression, which you probably completely don't remember any of the math, and you just call something inside of a computer that gives you those numbers. But these are the numbers that it gives you, right? When it says like, oh, we fit a model, right? It gives you these coefficients for the linear terms of this model, which basically says if I increase this variable by 1, this is how much I expect y to be increasing, right? It's just a slope. Now, I just talked about how we can go to any polynomial, and now we go to multivariable. Can't we just, do the same thing, right? So for any function, for any number of variables, we can just create a polynomial that is in all of the variables, and that will give us, it's a representation of any possible function, right? And so isn't that great? We can learn any function between any amount of inputs to any amount of outputs. All we have to do is you just have to write down a high enough order polynomial. QED, mic drop, like there you go. That's all you need with machine learning. But what's the problem with this polynomial way of thinking, right? It is an easy way to kind of get to like, oh, I want to learn a relationship from y to x. So therefore, write down a functional form that it's a representation of all possible functions. And now I just got to learn the coefficients in there, and I've learned the mapping, right? I have a representation. It's cubic with respect to this variable. It's linear with respect to this one. It's every possible thing that you can imagine as long as you put that high enough. But the issue with doing this is that the number of terms that you have grows exponentially with the number of inputs. So so what do I mean by that? Well, there's the exact formula right there. If you have k variables to degree n, then you have k plus n, choose n minus 1 variables, which, again, this is the non-math version of the talk. So let's just put a number in there. Let's just see what it's like. So let's say you have 100 predictors. Let's just say you have 100 predictors for this example fish problem, right? So you have the amount of algae in the ocean, you have latitude, longitude, you just have 100 of these things, and you want to learn what is the prediction of the fish population given these variables. So with 100 of those, you go, well, yeah, my function's more complicated than a line, so I'll make it, cubic? That should be fine. And so, okay, so Taylor, the multivariate Taylor expansion tells us we can, just make the polynomial degree high enough, and it'll fit any, pretty much any function. So let's do this on a cubic, and you can see that all the number of terms that you have in that polynomial, if you have 100 input terms, and if in a cubic polynomial, is you have 176,850 terms, right? That's called exponential growth. So if you begin to add more and more input terms to this, it's just going to keep on growing exponentially. Because if you look at the number of terms you have in this representation, right? What is happening? Well, every time you add a new variable, you have all the combinations. So if you think about the quadratic, right? The quadratic has, I wrote this out explicitly, just be x1, so that way it's easy. That's x squared, right? So you have x1, you have x1, x2, you have x1, x3, right? The second term inside of this polynomial is every variable matched with every other variable, including itself. The third one is all combinations of three variables. All combinations of three variables, all combinations of three things, when you have 100 of them, is a lot of things. Again, it's 170,000 things, right? 176,000 things. If you just have 100 things and you want to find all groupings of three of them, combinatorics grows exponentially, right? So this is really the core problem in machine learning. It's what we want to do is we want to be able to learn relationships we want to be able to assume mathematical relationships as a single function between our data to our output, and we just want to learn what that function is. Now, we think that this is great, right? If we could just write down a function that works for every single case, then it just becomes a math function of how do I find the numbers that go in there. But you very quickly run into problems where you can't write down these mathematical representations that mean every possible function, because the number of numbers you have to have for that is huge. But that's what a neural network is, right? So, if you've ever learned neural networks are things that kind of match the human brain, or crumple all that, throw that in the trash, right? What is a neural network to someone who's actually doing science, right? A neural network at a very concrete level is the same exact problem, right? You want to learn y equals f of x. So first thing, a neural network is a function, right? It's a function that takes in x and it spits out y. What does that function look like? Well, I'm just going to write down the very basic form of a neural network. So you've taken a vector, you do a matrix multiplication, you add a vector. You then do some nonlinear operation on it. You multiply it by a matrix, and you add a vector. That's it. It's matrix multiplications, matrix addition, or vector additions, and some nonlinear function, where many times that nonlinear function is rather trivial. Right? So why is that function making people so scared that it's going to take over the freaking world, right? Like, why are people scared that ChatGPT that's running this mathematical operation is going to, make it so that way you don't have to work again in the future, right? Why is this making people so scared? The reason is because of this thing called the universal approximation theorem, right? So the universal approximation theorem says this. If you make the matrices inside of there large enough, right? So I didn't really define all the details there, but it's a matrix of numbers, right? Kind of like with the polynomial, there's a lot of coefficients in there. And if you make that be large enough coefficients, if you just make there be enough numbers inside of there, then you can find numbers that are close enough to any possible function. Right? So what I mean by this is, if you make this be an object where you just stuff enough numbers in there, right? Thinking just like the polynomial case, right, where you have a1, a2, all these different slopes. If you just make these big matrices of numbers have enough numbers in there, then any sufficiently nice function can be modeled by that function right there, right? So that's the core reason why people are interested in neural networks. Because if your neural network is big enough, it can find any mathematical relationship. But wait, polynomials can do that. So why do we care about neural networks specifically and not just use polynomials for everything? Well, the reason is because this solves the curse of dimensionality, right? And what we mean by the curse of dimensionality is that as the number of inputs grows, then the number of terms that are required to be able to match a function grows polynomially, not exponentially. Which means that if you have a whole lot of inputs and you want to learn a function to a whole lot of outputs, what you can do is you can specify a neural network. And what you're mathematically guaranteed is that if the neural network is sufficiently big, sufficiently deep, like the big neural networks that people are doing today, as long as that neural network is big enough, it can learn any mathematical function that relates x to y. It can be, given the text that I've already seen, predict the text that the person wants to see that comes out. Given the pixels of a picture, predict whether this is a cat or dog, right? All of those are just mathematical functions, right? Where you say, okay, y equals dog, y equals 1 is dog, y equals 0 is cat. Learn a function from these input values to cat versus dog, right? These are all just learning mathematical functions. And what we've done is we've just found, hey, here's a nice mathematical form that has this good ability to approximate any possible function. And that is what a neural network truly is at its heart. If you ask it, neural network, what does your soul feel like in the morning? And it's like, it will tell you, I feel like any possible function, right? So, okay, so that is what machine learning is all about. It might be a very different version of machine learning than something like Elon Musk will sell you, but this is like what machine learning is truly all about. And now, where did our science go, though? Right? So in that whole description, I just told you, like, oh, you can learn literally everything, right? You don't need to know anything. Just give me your data, and I will learn everything for you, right? But the science has now gone out the window. Right? So now the whole thing about scientific machine learning is how do we bring the science back into the machine learning, right? So because you know things that are not in your data, right? Surely you know at least one thing that you know is not in your data set, right? Name something. Name one thing that you know is true, but you don't have the data to be able to say that it's true. Anyone in the audience here? Okay, the reason why I'm asking is because my examples here are not necessarily in Julie EO, but are in Earth observation. So the example that I would bring up is general relativity, right? We all kind of know that general relativity is true, but maybe you've heard Neil deGrasse Tyson tell you that it's true, right? But you kind of know that it's supposed to be true, right? But if you want to train one of these objects, you want to train one of these neural networks, it's going to learn y equals f of x from data, right? And so you go, okay, do you have a Google-sized data set of, 3 billion inputs to 3 billion outputs that gives you general relativity? No. I mean, but there's some experiments that we know that there's a small experiment here that shows it's true, small experiment here that shows it's true, and there's just been a whole 80 years of human math and science that have shown us this law is true. But there's no single data set that we could train a neural network on, and so no neural network will actually know this thing is true. This means we've done something very wrong. We've lost the science, right? And so the real question that's going on with scientific machine learning then is there's all this stuff going on in data science, right? So in data science, we take in data and we learn functions from it, right? This is what we're doing. We're doing machine learning. We're using data to learn functions. But there's this other part of science that we've been doing for hundreds of years as well, which is building models, right? Models that like general relativity, Newton's laws of gravity, these models that are, I know that a lot of people in biological modeling, you have these models that are, looking at bifurcations, and they tell you something, very true about what's going on in the world. And the issue is none of that is captured in our machine learning. We throw that all out the window, and we say, let's just learn everything from data and hope we have enough data. And so what we're doing with scientific machine learning is we're going, no, that's crazy. That's crazy. Like, our scientists, we know things, right? So how can we bring in what we know to be able to make the data that we're using work better? And so I'm just going to talk about like one example type of way that we're doing this. There's many different ways that we're doing this. But one way that we're doing this is something that we call the universal differential equation, with shorthand for the universal approximator differential equation. So here's an ecological model, right? It doesn't look like an ecological model, but let X be the number of bunnies and let Y be the number of wolves, right? So now this is a form of the Locke-Volterra model, right? Where I say, well, if you let the change in the amount of rabbits over time will be positive in the number of rabbits. Rabbits tend to make more rabbits. That's something that we know. And wolves, if you just have wolves in a room, you just tend to get less wolves in a room over time. No one really knows what happens there. But if you put rabbits and wolves in the same room, my mother really never told me how to finish that story, right? So I don't know the mathematical model. So what do I do at this point? Well, if if I don't know how to complete my mathematical model, how do I write this into a computer, right? I need to, if I want to simulate it, if I want to get plots, I got to write down a function, but I don't know what function to write down to finish this model. But wait a second, don't I have something that can represent any possible function? That's what a neural network is, right? So there you go. So let's just say, a neural network is just a function. You throw in some values, it spits out some values. Here, what I'm going to do is I'm going to say, I put in the values for number of rabbits and number of wolves, and what will spit out is how much the rabbits and wolves are changing in a way that I did not capture in my current mathematical function, right? So at a high level, what I'm really doing then is I'm saying, hey, here's my mathematical model. I've written down everything I know how to model, but the piece that I don't know how to model, the physics I don't know, the biology I don't know, the chemistry I don't know, let's only learn that part that I don't know via a neural network. And then you get to schemes that look like this, but again, this is not the nice mathematical audience that wants to go into figures like this. So let's just go example by example instead. But what we're going to do is we're going to come up with a method that will take in data plus neural networks mixed into models, and it will basically autocomplete models. If you think about it as like, you type into Google, like you'll type into Google, you'll be like, what is, and then then it'll autocomplete you. It'll be like, what is the proof that the Earth is round, or something that whatever Google's spitting out that day, right? What we want to do is we want to do that for science, right? How do we do that for science? Well, let's do this on a simple example. And the example that I like to show for this is it comes from epidemic modeling. Why did it come from epidemic modeling? Because I happen to be working on this in 2020, right? And I think everyone here kind of knows a bit about epidemic models these days. It kind of impacted a few people. So let's start there. So here is an example of early in the COVID-19 pandemic, right? So early on in the COVID-19 pandemic, you had the pandemic start in the Wuhan region, and here's the first 60 days of that data, right? And now we want to learn, okay, given the data that I've seen, let's predict in the future how bad this pandemic is going to be. What kind of function is it? It's just y equals f of x, right? It's just the number of infected people, the number of recovered people, the number of exposed people. That is a function of the current number. It's a differential equation that is a function of the number of people that are infected today, right? If you have more people infected today, then the change in the amount of people who are infected probably goes up because you have more people to infect other people, right? So there's a mathematical relationship in there describing the change, and then we just extrapolate that change, and that's how we could get this function, right? So let's do machine learning, right? Okay, we want to learn a function. We want to learn a function of change. Let's just do u prime equals neural network of u, right? So what is this? This is now this thing called a neural ODE. It's just a neural network that is just writing down an ordinary differential equation, right? Just a mathematical function where I didn't know what to write on the right-hand side. So I just put a neural network there because it approximates any possible function, so let's do that, right? So if I do that now, and I train it on just 21 days worth of data, so I train it on the data up to that line, it looks great where I trained it. It's because, it can learn any possible function, and it learned a function that goes right through my data points. Beautiful. And then we see, COVID GPT, what do you believe is going to be the number of people who is infected in the future? And it extrapolates like that line, and my data points are like that. Ouch, right? But have you ever done some data science with machine learning? You've seen this before, right? Machine learning with small amounts of data does not capture a lot of this behavior. And there's no reason for it to, right? Again, at a concrete level, what did I actually do? What I actually did was I said u prime, so this differential equation, equals any possible function. So give me any possible function, and that fits this data right there, and let's just see what happens in the future. And it goes, oh, here's one function that fits your data, and I bring it to the future. And you're like, that is true. It did exactly what I said. There's nothing wrong with the math there. It did exactly what I said, but what I said isn't necessarily what I mean, right? Because what I mean is, well, what do we know about pandemics? Well, at the start of a pandemic, you have an exponential growth, right? Then you probably have at least one peak that happens. And then you have, there's a lot of things that we know about pandemic. Or you're not even a pandemic researcher, and you know that there's exponential growth before a peak, right? So can we tell our neural network that stuff has to be true? Turns out that we can, right? So what am I showing by this? Well, you might have seen these kind of things like SIR models, right? Susceptible people become infected and then recover. You might have seen many of these different models during the pandemic. Well, here it's a bit more complex of a model, right? So SEIRD model, what does it mean? Well, this is a mathematical model that people have developed that says susceptible people become exposed, exposed people become infected, infected people either recover or die, and people who are exposed, they get exposed by people who are currently infected. So this is a mathematical model that people have come up with to be able to study pandemics. And so you might go, well, if this is a mathematical model that seems to model pandemics pretty well, why start our neural network with nothing when we know that this is approximately true? So let's just start it there. So we're writing down this SEIRD model. So susceptible people become exposed, people who are exposed to the disease become infected, yada, yada, yada. Now, the difficult thing here is that how do you actually write down the exposure term, a nice mathematical function for how people become exposed to COVID-19? Right? I'm pretty sure that everyone in this room had a very different experience with COVID-19 from each other, right? If you were in Sweden, there was no lockdown. If you're in China, there was a completely different experience. If you're in the United States, it depended on which state you were in. In some states, COVID-19 didn't exist and was just a government conspiracy. In other states, it was, the biggest deal ever. You didn't leave your house, right? And so how do you put that down into one function that says, this is the mathematical function for people, how people got exposed to COVID-19 in this country? Right? This is a very difficult mathematical function to write down. I don't know how to write it down. But do I have a tool that will let me write down, this magical, any possible mathematical function? Well, I do have that tool. That tool is the neural network. Right? So what I could do then is I can take a mostly complete model of COVID-19. So that I take this SEIRD model and I say, there's this term that people write in there that's exposure. And when you do your mathematical modeling, you would say, oh, I assume that the exposure is this. And when you make those assumptions, it changes your model around. Well, here I'm not going to make any assumption about what the exposure function looks like. I'm just going to say, I don't know what it is, so make that spot right there be a neural network. It takes in the other values, it spits out a value right there, and then that is just what is the current exposure rate. And if I know the exposure rate, then I have a complete mathematical model, right? So I have a mathematical model where I filled in one missing function with a neural network. This is the kind of the core scientific machine learning. I'm writing down everything that I know. I have a full model of the system, except a few bits. So let me just learn what those few bits are, right? I'm recognizing that I have some prior knowledge, but I'm just using a function approximator to approximate the functions that I don't know. And you can see that it instantly does quite a bit better, right? So if you look at the top right there, that's the machine learning that we had before, this neural ODE, learning completely from scratch. It does not have a happy day. But if you look at the second one, this universal ODE extrapolation, you see that from 0 to 21 days, it learns up to how to predict reasonably well up to 40 days, right? Again, because it's encoded the mathematical assumptions that we know about the model. A mathematician can go in here and actually prove that if you take the absolute value of your neural network's output, then you actually have an exponential decrease in the number of people who are susceptible, which ends up making that you can prove that there's then a peak. So that way, there's one peak in the number of people who are exposed, and that gives you actually one peak in the number of people who are infected. So you can think about this instead as here's a mathematical representation that has an exponential growth in the number of people who are infected early on, an exponential decrease in the number of people who are susceptible, and it encodes that the function must have a one peak in there in terms of the number of infected individuals. But it actually has all these things have to be true about this function, no matter what the neural network is. Now, learn the neural network that gives a pandemic that looks kind of like that, right? Now, think about the difference, right? In the first version, you didn't even have to have that, the number of people stays the same in your model, right? It could go to anything. The neural network literally is learning any possible function. But here, since I'm subtracting the same term that I'm adding, the number of people is conserved, right? So the number of people in this model, everyone's either infected, recovered, or dead, right? Everyone is accounted for. So all of these things that we kind of know to be true, that just have to be true because of what we're modeling, they're all constrained to be true by default, and we just tell the neural network, fill in the details, given that I know that this is true. And now the final piece, which is a bit of mathematical magic that I won't go into how we do this, is a symbolic regression aspect, where we then say, well, once we've learned a neural network, can we turn neural networks back into polynomial functions, right? Because again, remember, polynomials can represent any possible function. So once we've done a huge training process to learn a neural network, can we find a simple representation of what that neural network learned, right? And here what I'm saying is, oh, it learned a function that goes I times that number plus da 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 da. Slap that in there, right? And there you go. What you then get is you get this process where you've written down an equation. You then take that equation to your data with some missing parts with neural networks, and you say, find what's missing for me. Find it in terms of a neural network, and sparsify that down. And now it will basically done the Google autocomplete, but on your mathematical model, right? And this is what we're then doing with scientific machine learning. You can see that there's two things that you get from that. One is that you get explainability, right? So, a lot of people that do mathematical modeling, you can look at this and see, exposure was allowed to be a function of S and I and D. And you know what? The function for exposure there actually doesn't end up to be a function of D at all. What does that mean? Well, it means that the people who have already died from COVID-19 are not the people infecting new people. Our neural network has learned something, and that we can, that's something we read directly off of the equations right there, right? And it's reasonable. So you get some explainability from this, and you also get generalizability. What do I mean by generalizability? Well, again, it's learning from the same data from 0 to 21 days, extrapolating it out. It's not perfect, but it's learned a much better function than the other functions that were learned before, right? So again, from the same amount of data, you can get more mileage out of it by bringing some scientific experience or expertise into it. So that's really the core of what we do with scientific machine learning. And so there's many questions that you can have with this, right? So let me go back to this kind of picture that I had here, right? So this picture that I had here is this kind of, if you want to make a good prediction, what you want to do is you want to pour knowledge in, right? And you can pour knowledge in terms of models, or you can pour knowledge in terms of data. And this kind of gives you an idea that maybe they're kind of like one-to-one, right? If I'm saying, there's a knowledge content of data, there's a knowledge content of model, so maybe I can just kind of choose how much model I have versus how much data I have, right? And that ends up being what we can show with scientific machine learning. So, given all the different work that we had in the pandemic, et cetera, I think we can boil it down to just a very simple result, which is just, the more prior model that you know about your system, the more science that you're bringing into the system, the less data that you need in order to make a good prediction, right? Or another way of saying that is, from the same data, if you add more scientific knowledge to the model that you have, the scientific machine learning approach will be able to make better predictions from that same data with the model that has more prior knowledge added to it. It's something that you might expect to be true, right? The more we know about science, the better predictions we can make. But, at a very core empirical level, this shows that, if you do this with, this neural network approach and all that, that core idea that you know to be true really does work out to be true. And so there's some papers that kind of show that aspect, but that's really then the key behind scientific machine learning, that we want to bring in as much prior scientific knowledge as we can, so that way the same data that we have is learning more accurate functions. Now I'm a bit behind, so I'm going to skip over some things that look kind of cool, right? So there's, how are we using this? So we use this so that way you can assume Newtonian mechanics and you learn general relativity automatically, and all this kind of fun stuff, and yada, yada, yada. We put it on cell phones and yada, yada. I'm way behind, so I'm going to skip over some details. And we did use this for the COVID-19 vaccine and things like that. Yeah, da, 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 da. So in the end, So in the end, what are we actually doing? Where does Julia come back into the story? Well, what you then need in order to do all this is you want a stack for scientific modeling that lets you just mix it with neural networks, right? Because, what are we doing that's different here? Well, what we're doing is something where we say, I don't just have neural networks and data spit out the data, right? What I want to do is I want to take the mathematical model. You want to be able to do things like say, take the model that you have, like a global circulation model that is representing climate, right, and climate change. You want to take that and say, well, we don't actually know how the relationship between, phytoplankton and the albedo works. That's somebody's guess that they wrote in the model. So replace that guess with a neural network and learn it in that context. Yeah, the whole same spiel. We want to do this with as many complex models as we can. Now, what's the difficulty? Well, prior to Julia, a lot of people were writing these mathematical models in C or Fortran because that's how you get performance. And we're like, no, we got to be able to mix the machine learning. You can't just assume they got some guy, like I think a lot of people have a lab where you say like, oh, there's some guy over there. He works on the climate model, and no one really talks to him except when you need results, but he knows how to run this thing, right? Or maybe it's your old professor. Like she is really good with Fortran. She uses this code. We passed it down from generations to generations. No one else knows how to modify this code, right? If your code is like that, you can't mix machine learning into it. You can't do all this. So this is where we say, okay, we need a new software stack. And this is where Julia's SciML comes in. So, if you think about like what is SciPy or what is MATLAB, we think about, though SciPy and MATLAB, they're things that have mathematical solvers, right? Mathematical solvers for, AX equals B, for, if you give me, function f of u, find the value of u such that it equals 0. That's a nonlinear solve problem. There's ODE solvers, things for doing optimization, right? There's just a bunch of mathematical solvers. And what we are doing with SciML essentially is saying, well, we don't want to keep those separate from the world of machine learning, right? Because you might build your model as a set of algebraic equations. You might build your model as a solution to an optimization. And if that's your mathematical model, what you want to do is you want to be able to say, let's take that function in there, or that function, or that function. Let's take a function that's inside of our model and put neural networks inside of it, because that's how you can represent, I didn't know something in my model. So what we need to do then is we need to be able to take any kind of solver that exists in the ecosystem and make it compatible with machine learning, which doesn't exist with anything else. If you go to SciPy and if you go to Python, right, you got like PyTorch and then you got your SciPy. And these are two different things. If you put the neural network inside of the SciPy, it will not know how to differentiate this, right? And so what we've done with the Julia ecosystem is we've gone through and to be able to make this solver stack that is completely composable, so that way there kind of is no difference between what people use for scientific modeling and what people use for machine learning. So that way we can do all these connections and be able to use them together for these scientific machine learning approaches. And not only have we done that, I think we've done a pretty good job. Here's an example of, for the ODE solvers, this is kind of what we're known for with a lot. Here's an example that shows 50 times faster than SciPy, 50 times faster than MATLAB, 100 times faster than R's DE solve. And so, if you're also, as you do these models, you're throwing neural networks into them. The models get big and get expensive, and so we've worked a lot on getting this performance, so that way very large models that you're learning and you're churning through it, doing this process on, can be fast enough so that way you can get this autocomplete in a reasonable amount of time. Also, everything works with GPUs, yada, 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 and for lots and lots and lots of different kinds of models. But the key here really is then, you can kind of take whatever kind of mathematical modeling you're doing. If you do some mathematical modeling, you can take however that model is written, and you can use this idea, right? You can say, well, I know that this term is good, but this term is junk. I actually knew that this scientist was drunk when he wrote down this thing, and he just published the paper anyways, right? And you're like, I know that this term doesn't make any sense. Everyone in the field knows this term doesn't make any sense, but what term should go there, right? Well, you could put a neural network there. You train that neural network in the context of all the other mathematical knowledge that you have. And what you'll learn is you'll learn how to autocomplete these functions, and that gives you a predictor that you can use as part of the scientific process. So I think that this is a way to think about learning in science and machine learning in science that is more scientist in the loop, right? You're using it as a tool for being able to increase the speed at which which you come to understanding, rather than trying to treat it as a black box that just learns, input, output from large sets of data. And I'll leave it there, so you can go check out the Julia SciML tools, and if you have any questions for the kind of mathematical models that we do, we probably have worked on solvers according to that. And I think I'm about at time, so I'll take questions from the same mic I've been walking around with. Thank you. Oh, don't worry, I got an empty. It's early in the morning.
Hey, thanks for this great talk and for all the great community, contribution that you do to the Julia community. It's really great. I was wondering about these coupling the neural network with dynamical models. So most of these neural network techniques are based on the gradient of a loss function. And one problem that you could have is when you have a chaotic system, is that the gradient is not really reliable. So if you have even small initial condition change leads to a big change later on. So I'm just wondering if do you think it's a fundamentally unsolved problem, or what could we do in order to use useful gradients in such a context?
Well, let me start to go through my files here. So when I said that this is the non-mathematical version of the talk, I dropped off like, what do you do about, if you want to take auto differentiation of ergodic systems and things like that. But that's what I find to be the fun part of the talk, right? So let me bring in this presentation that has that. To do one of the presentations that has that is. Yeah, so I also want to show like, we also work with the Williams Formula One team. So if anyone likes Formula One and likes Julia, this is the car to root for. We started doing a lot better these days. So, yeah. But other random things going down past climate models too. Yeah. So here, this is talking about. This is a slide that's all about this exact graph, right? So one of the key things is that if you have some models, so what I completely skipped over is I didn't tell you at all how I train these neural networks, right? Like I just said, you slap a neural network into a model, and then magically, when that neural network is trained, it's a good model, right? But there is a core detail in there, and that core detail is how do you train these neural networks? And this is where the science of in math of automatic differentiation comes into play, right? So the whole software under the scenes is how do I calculate derivatives of solvers? And this is an interesting topic because not every way that you calculate derivatives of solvers is actually you can write down things that are mathematically true that are not numerically true, right? You might have had your professor tell you before, like, no, you've written down something that is numerically unstable, right? Turns out that it's very easy to do with derivatives. In fact, we went to the Python library. We wrote a whole paper that basically said their library calculates wrong things whenever your function's stiff, right? So you could go see the published paper all about those details, right? But so one of the other cases that really comes into play with this then is how do you do this training if it's on a chaotic system? Because if you have a chaotic system, very small changes in your parameters or in your initial condition end up giving you O of 1 changes in your solution after a given time, right? So it turns out that actually that derivative is not well defined, right? Because the solution is not really well defined. But there's actually a very funny property that you can use. If you have a small, so there's something called the shadowing lemma, right? Which is that if you have a chaotic system, then within an epsilon space around your point, there's another point that your numerical method is actually exactly solving for, right? So you know that your numerical method introduces error, and your errors grow exponentially. And so what you're looking at on the screen when you put in, say, the Lorentz equation means nothing to do with your actual equation. You can prove that your error is O of 1, right? But you can also prove that there's actually a point that's right nearby it that gives you that you've actually done the real solution for. And this is the shadowing lemma. So you found a shadow trajectory with they say, right? And it turns out that you can use that fact to come up with a useful form of automatic differentiation on chaotic systems. And the way that you do this is you start to say, well, I cannot take the derivative with respect to, the value of the solution at this time point. But if I look at the average value over all time, for example, like the Lorentz equations, right? It gives you a nice picture of the butterfly wings, right? And if I change my parameters, those butterfly wings will move around. And so the average value of x is actually a well-defined quantity. The average value of z is a well-defined quantity. And you actually define these new forms of automatic differentiation called shadow adjoints, which are giving you the derivatives with respect to these average quantities of chaotic systems. And if you do that, then you can learn directly from chaotic systems, from their data, even though you know that simulating from one point to the next, there's no way to actually be able to do that. But statistically, there's some things that have to be true. So there's so when I do the mathematical version of this talk, it all comes down to a question of how do you calculate derivatives accurately to train these things. One of the things that we talk about is chaotic systems. The other thing that we talk about is the other completely different form of models that people do, which is agent-based models. So how do you come up with a derivative of agent-based models? And that's its own topic itself. But we created a new automatic differentiation library so you can do the same thing with agent-based models. So if you then create an agent-based model and you say, I don't know what function is, the rate at which, people get infected, you can put a neural network there and then train that in the same exact way. So yeah, so if you have any derivative questions, I'd be happy to go into them in detail, but I already went over. So if you no one gave me a whiteboard in 3 hours, so if you gave me a whiteboard in 3 hours, I'd love to do this, but yeah.
Thanks for the talk. Very, very nice. Can you just comment on that conversion that I started, which showed that you get the neutral to universally and then the internal sparse progression? What is the internal sparse progression?
Yeah, so so you can. I think that the easiest way is to kind of just check out the library. So you have data-driven diffeq.jl, right? So what am I doing here? Well, the Julia SciML libraries have documentation. Wow, much nice, right? And so one of the libraries within here is data-driven diffeq, which is all about this kind of what we call symbolic regression. We're actually working on a lot of new tools for this. There's this Miles Kramer has a nice symbolic regression.jl. We're building a new model discovery.jl, which is kind of mixing the two of these, but that's a whole details. But yeah, you can go to one of these libraries, and what they do is they can, you give it a small data set. And what it does, then it spits out the predicted functional forms for, there's restrictions to this, right? You need to tell it a basis set to live in. So you say, okay, polynomial basis of, fifth degree polynomials of these variables. It won't scale as well as things like neural networks. And so there's a reason to use the two together, which is kind of a deeper topic. But yeah. So what it's essentially doing, if you want to think about, what is some of this doing, right? The methods get very complex, but the simplest one is STLSQ, which is sequential thresholding least squares. And what sequential thresholding least squares is doing is, that if you do a lasso regression, you get less terms, right? And so what you could do is you could start to say, well, I'm going to write out a linear relationship between all of my values in my basis function. And I'm going to do a lasso regression. But I'm going to do this with sequential thresholds, right? And my thresholds are going to be exponential to the 10, yada, 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 right? So you do a lasso regression, and anything smaller than this value, you chop off and make it 0. And then you do the next lasso regression with a higher tolerance, and then you make those equal to 0. You keep on doing this through the tolerances, and the terms that remain is a representative mathematical model. STLSQ is one way of doing it, but then there's a whole libraries of more sophisticated ways.
The neural network that was obtained from the
yeah. What's a way to look at this, right? So I want to learn, say, the function that I want to learn the function that goes right there, right? So what I've done is I've learned a neural network, right? So neural network is now y equals neural network of x, right? And I want to then know what function goes right there. So I've learned. So what I've learned is I've learned actually a functional representation. If I put in x, it gives me what value goes right there, right? So what I can do is I can just put in a bunch of new values of x and create a data set, right? I create a data set that is, what is this missing term inside of my model, right? So now I've essentially translated data about the number of people who are infected to now give me a data set of number of people that are infected to what the correct exposure rate is. And once I have that data set, I can run the lasso regressions. Yeah.
Hey. Thank you for the talk. I also have a question. It was really good. So let's say you have a more simple system where you just have some inputs you map to some outputs, and it's not PDEs or like these complex dynamical systems, but you have an idea of like some of the functions that go into there. Would it still be useful to use the SciML approach, or would it be overkill when you have once it's not a PDE system anymore?
Yeah, so I tend to talk about ODEs and PDEs because the whole world is ODEs and PDEs, and I love it, right? But there are a few things in this world that are not ODEs, and that upsets mathematicians, right? But yeah, so if you have some other kind of model, you still tend to have some kind of mathematical model, though, right? A lot of times it could be like, say, a nonlinear system, right? So an equilibrium model is a model that is f of x equals 0. Find the value of x that makes this equal to 0, right? So general equilibrium models that you have in biochemistry and things like that, they still have some mathematical mathematical model, and you have a solver for it, right? You use fmincon if you're in MATLAB. You use fmin, and I think that's what it's called in SciPy, right? You use these functions that essentially find this x that causes your model to be equal to 0, and from that you find the equilibrium chemicals and all this, right? Those same that you can actually do all of what I discussed here in that context, right? So you just say, here's my model that I know, here's my model of the chemical equilibria. I don't know one of the equations that goes in there. Maybe one of the chemistries is not well understood. I make that be a neural network, and I just need to be able to solve the nonlinear system with the neural network inside of there. But it's just a function, so I can do the same thing. And you can train the neural network in this context and use that to be able to tell you what piece is in there, right? You can do that for nonlinear systems. You do that for optimization. So I know a lot of people do like things like convex optimization, or there's many different ways that people write down mathematical models. And all the different ways that you can do mathematical modeling, whether it's the integral of a term or whether it's a convex optimization, all of these different ways you can write down mathematical models. If you can mix them with a neural network, then you can do the same idea and you can extend it to the modeling that you're doing. And so yeah, that's what we work on in the SciML organization, making it so that way the whole suite of solvers is available with this. We haven't done it with every type of solver. I think convex optimization is one that we haven't done as much with. But we're working on getting the whole solver ecosystem compatible with neural networks, so that way any scientist can do that for their type of model. Yeah, and we can speak more about your specific model afterwards if you want to kind of think about like what are ways to kind of do this thing.
Okay. Thank you very much again.
Thank you.